Just check for prior knowledge question for this unit. Okay, so what do you think of when you hear what you think? Gotta go change that typo. Oh no, it's not. Write down what you think of when you hear the word energy. Okay, what do you think of when you hear the word energy? And then which of the following below has energy? A car that's at rest or a car that's moving? One, the other, both, or neither. Okay, please take a second to answer, along with a brief justification for your answers. So today we're looking at energy. We're starting our new unit where we look at energy momentum. Two very similar but subtly different concepts. So in this unit, or specifically in this lesson, we'll take a look at what energy is, how we use it in physics, and what the different forms of energy are. So some announcements. There are no immediate announcements forthcoming. All right, I hope you all have a great Thanksgiving break. Please save me some turkey and a slice of pie. So what we're up to today, defining what energy is, establishing the foundations from which the rest of the course will be built upon. So we looked at kinematics and forces, okay? Those are two central concepts, but really, building off of forces, there's one concept that it becomes very, very, very important as well, and that is energy. Momentum is also a big one. So kinematics, force, energy, and then what we'll look at after energy in this unit, momentum, are the four big things that establish the foundations from which the rest of the course will be built upon. And then lastly, we'll explore different types of energy and how and where we encounter each type of energy. So the first thing we need to establish is what is energy, okay? So we have this idea of what energy is. It's something that it's hard to define even in everyday life. If something moves, we say it has energy. If something is moving really fast, we say it's energetic. We say we use energy, like energy from windmills or solar plants, to power things, okay? But in physics, we have to establish a bit of a formal definition for energy, okay? So energy in physics is a transferable physical quantity that, when possessed by an object, allows the object to move. This isn't the official definition in physics, but the official definition in physics is quite circular. So this is a very conceptual definition that allows us to envision what energy is, okay? So when we say that's a transferable physical quantity, we don't mean that's something that you can hand to another person, like you can hand a rock to another person, or you can hand money to another person. Energy is something that we can't exactly see. It's not exactly tangible. Just like velocity and force, it's not something we can see. It's not something that's tangible. But we know that it's there. It's a physical quantity, and it's a quantity that we can transfer from object to object when possessed by an object, or that when possessed by a certain object allows that object to move, or better said, the capacity to move. So unit we use for energy is joules, spelled Joules, named for, I believe, I always forget his first name, I think it's Charles Joule, but don't quote me on that, who was an English chemist and physicist who was responsible for developing the idea behind energy, the concept of energy, okay? So I'll give you a second to get this down right here. All right, and if you're going to wonder how does energy get transferred from place to place, that is going to be one of the concepts that we look at in this unit. How does energy get transferred from one place or one form to another place or form? So back to the basics, all right? So let's consider these examples here. Do these objects have energy here? So this red car doesn't seem like it has energy. This blue car definitely has energy because we'd say that's moving. We associate energy with movement, okay? But does this red car have the capacity to move? This red car does have the capacity to move if you put your foot on the accelerometer of it. So the car has the capacity to move, thus it must have energy, even if it doesn't seem like it has energy, because it's not moving. So energy can be stored in an object, allowing it the capacity to move, even if that object is not moving. So what do we call this energy that's stored in the object? Well, in this case, the energy being stored in the object would be the gasoline. The gasoline goes from the gas tank to the engine, is converted into a form of energy that we can use to move, causing our car to move. So we still have energy that's stored in the form of the gas that's in the gas tank. So what do we call this form of energy that's stored? All right, so that's what we'll take a look at down the line in this unit. So for right now, for the first type of energy we need to establish is the one we're most we are most familiar with, and that is translational kinetic energy. All right, which is energy due to an object's motion from one location to another. So any object that's moving in the universe has kinetic energy. Okay? It's defined by the equation below where m represents mass and v represents speed. So kinetic energy is equal to 1/2 times the mass of an object times the speed squared. And we call this translational kinetic energy because there's different forms of kinetic energies, as we'll see in a second. Translational being the form of kinetic energy when an object moves from one spot to another. The second form of kinetic energy we have is what's called rotational kinetic energy. Okay? It's an energy due to an object's rotational motion. So if we consider this windmill here, these windmills are not moving from one spot to another like the car was doing on the last slide, but the windmills still have motion and rotation. So there's no translation going on. Our windmill's not moving from one spot to another, but still has motion in the form of rotation. So it does still have motion and it thus has kinetic energy. This is what we call rotational kinetic energy. We get real creative with the names here. It's energy due to an object's rotational motion. So it is possible that an object, as we've just talked about, can have rotational kinetic energy but no translational kinetic energy. So for example, again, like we just talked about, windmills can have rotational motion but are hopefully not moving from one place to another, because that's probably not a good thing. So now we come back to this idea of energy being stored in an object. What do we call that? We call that potential energy. So energy is stored in an object is what we call potential energy. It gives the object the ability to move if acted upon by an external force. So different types of potential energy. There are gravitational potential energy, electrical potential energy, and chemical potential energy. Okay, so we'll explore electrical potential energy in a later unit, but let's look at gravitational and chemical right now. Okay, so gravitational potential energy. If we have two people that are on a ski slope, we would say that both these objects have energy, even if the skiers are not moving. The reason being is that they have the potential to move by falling down the slope. Thus, there's energy stored in them due to gravity. If gravity starts acting on these skiers, the skiers are going to fall, and thus they have potential energy because they have the potential to fall and to move due to that force due to gravity. In this case, the blue skier is going to have more gravitational potential energy because the blue skier is at a higher height, which means our blue skier has more potential to move, more potential for motion, which is reflected in the fact that if both these skiers reach the bottom of their tracks, the blue skier we'd expect to be moving faster than the yellow skier, indicating to us that the blue skier has more energy stored in them at the beginning and thus more potential to move. Now let's take a look at chemical potential energy. Perhaps you learned about chemical potential energy in chemistry class. So the idea behind chemical potential energy is that every time you have a chemical reaction, there's going to be some chemical bonds that are broken and reformed. And so if you have bonds that are broken but never reformed, the bonds breaking releases energy. So there is potential energy stored in chemical bonds of molecules, and when these bonds are broken, that releases heat and light as energy. And so that's like what we have with the car. The car has chemical potential energy in the form of the chemical bonds inside of the gas tank, inside the gas molecules. And when the gas is sent to the engine converts that, breaks those chemical bonds, which releases energy for us to use to power our car and move forward. Oh, and actually we do have an example of electrical potential energy. So electrical potential energy would be like prior to lightning striking, there's a buildup of electrical potential energy inside of a cloud, and then when that buildup reaches a high enough level, there is lightning that occurs due to the electrical potential energy in the cloud. So let's look at a wrap-up question here. Trains are more or less machines that take in coal as a source to produce motion at a very layman's level. They're more complicated than that. All right, so what forms of energy are present in this scenario? Provide your reasoning for each form, okay? And then from the perspective of forms of energy, Explain how a train might function. Draw a flow chart to demonstrate what is happening. So take a moment to answer his question, and you can pause if need be. So there's chemical potential energy stored in the coal, okay? The coal has chemical potential energy stored in the molecules that make up the coal, specifically carbon molecules, for those of y'all who are chemistry aficionados. All right, and then what happens is that the coal in the engine is burning, which releases energy in the form of heat. So those chemical bonds inside the coal are broken, which releases heat. And then that heat is used to power the train, which causes rotational kinetic energy in the wheels turning. And then lastly, we also have translational kinetic energy because not only are the wheels turning, but also our train is moving from place to place. And this more or less explains how a train works. If you have a flow chart on your sheet, that's fine. I don't have a flow chart here. But again, the basic idea is that chemical potential energy is converted into heat, being released as coal is burned. That causes the potential energy to be released and converted into heat. That heat powers an engine, which then causes our wheels to turn. So we have heat converted into rotational kinetic energy. And then we also have the wheels turning, allowing us to start to move, which finally gives us translational kinetic energy. So this is a wrap up for today for 4.1.